Hello community! In the next minutes we talk about why chain of thought and self-correction in our large language model fail and what we can do against this if we read the latest AI research literature. So let's start with the first paper. We have 3 papers today, and the first one is here from September 16 on the diagram of thoughts. And we have here Tsinghua University, real interesting paper. And what they do, they have a chain of thought, a tree of thought, a graph of thought, and now they develop here the diagram of thought. And you might ask, hey, I've seen almost no implementation in code of graph of thought. Almost everybody's talking about the chain of thought code implementation. So what is now this new diagram of thought? Can we actually use it? This is interesting. Let me have a look at now at the content of the paper. And what they do, they organize here their proposition, their critique, their refinements, and their verification now into a cohesive DAG structure. So this means a directed acyclic graph structure, which allows you the model to explore more complex reasoning pathways. So how do we build this? Each node in this new diagram corresponds now to a proposition that has been proposed, critiqued, refined, or verified, which enables now the LLM to iteratively improve its reasoning through a natural language feedback. And by leveraging now our autoregressive next token prediction with role-specific tokens, I'm going to show you this in a second, this diagram of thought facilitates now a seamless transition between proposing ideas and critically evaluating them. But this is not all, because the authors of this study here claim that they also developed here a theoretical foundation by formalizing here this diagram of thought idea within a mathematical theory, topos theory. So let me clarify here a lot, because we just go to GitHub, diagram of thought, prompt, iterative reasoner, and we look here at the diagram of thought, iterative reasoning prompt. So we say, hey, you are an AI language model employing iterative reasoning through 3 distinct roles. Each role encapsulated within specific XML tags. We have the proposer, we have a critique, and we have a summarizer. And then we just assign the roles and the responsibilities for the proposer, for the critique, and for the summarizer, plus we define the process flow. For my green grasshoppers, here you have the role and the next token prediction for the proposer, the critique, and the summarizer, and here the reasoning process. It is not really complicated, it is more or less what you are familiar with. However, the mathematical foundations are not trivial. The authors of the study refer here to this particular book. This is here Sheaves in Geometry and Logic, a first introduction to topos theory. I found it in MIT bookstore. It costs here about $85, and it takes quite some days before you get the book. Or, if you want it in a more recent approach, I just asked ChatGPT 4 Omni to give me a short introduction to topos theory, categories and functors, the definition of a topos. Topos is a specific kind of category that satisfies certain conditions, finite limits, exponentiation, and sub-object classifier. Then we talk about Grothendieck's topos, in algebraic geometry. A Grothendieck topos here generalizes the notation of a sheaf over a topological space, allowing for the study of geometric properties of spaces through categorical structures. But the application of topos theories is what we are interested in, and Grothendieck's original use of the topoi was to study sheaves in cohomology in algebraic geometry. And this is a framework for defining and studying this structure in more abstract spaces for logic and theoretical computer science. So if you are into this, I think this is a paper for you if you prefer the abstract algebraic geometric mathematical logic. However, there's a paper by Princeton and Johns Hopkins University and the University of Texas, September 18, 2024. Chain of thought or not chain of thought? So we are back to, you see, the chain of thought. So the simplest, there's no tree or the graph of thought. Everybody's talking only about chain of thought. Maybe the complexity of the other models is simply too high to be implemented in our everyday large language model. So what is Princeton now claiming? They say now that much of the gain that we see in our chain of thought prompt engineering comes now from improving through symbolic execution. But they say even this symbolic execution of our chain of thought underperforms if we compare it now to an external symbolic solver. Now, this is exactly here the second part what we would expect to some dedicated software package, but that the gain here from chain of thought come mainly from symbolic execution. This is interesting because this would mean that in our plain English prompt formulation, chain of thought would not contribute. Now, they did a lot of experiment, and you see here these little dots, and each little dot is a test if you want. And we have simple here, we have a positive x-axis and we have some negative x-axis elements. And what we look at here is the improvement of a chain of thought, would be here on the right hand side, over the direct answering. So let's see when is chain of thought on the positive side and when is the effect of using a chain of thought gives us here a non-performance of the LLM. So we should not use chain of thought in those cases. Now, easy, symbolic and algorithmic and mathematic. So whenever you have, let's say, an equal sign in your equation or in your task, in your prompt, then, as you can see here, my goodness, there are a lot of dots here, up to plus 60 here. So chain of thought is great. You can use it here in symbolic and algorithmic and mathematical and logical reasoning. However, the situation changes if you go here above other. If you have context-aware question and answer, or multi-hop question and answer, or you go here to knowledge, encyclopedic knowledge, you see there are a lot of result dots here suddenly on the left side of our red dotted line. So this means it is not so recommended at all to use here, think step by step and use here this chain of thought approach. Also for common sense reasoning, you see here quite a little bit shifted here to the negative side. And of course, do not do any classification of any text here with a chain of thought because the result can be up to minus 40 in the performance gain. So interesting that Princeton, Hopkins and University of Texas, they looked at this, they did a lot of experiments and they really tried now not to do our standard benchmark test that you see everywhere on every platform. But they say, hey, let's look at this from a different perspective. Let's really check if chain of thought is really improving here our performance. And they found out, yeah, in those cases, yes, and in those cases, no. Great. What they also find out that they said there's a need to move beyond the prompt-based chain of thought to new paradigms that better leverage here the intermediate computation. And yes, of course, the more we have here function calling, the more we have access here to external computer simulation, to programs, to symbolic solver, to Python environments. Yes, of course, we should use those tools that are available for us and not try to do everything within a LLM. And I found this visualization I want to show you here. This is real nice. This here, they show here the authors here, our experiments on chain of thought improvements. And you have in dark blue, the zero-shot direct answer, so no chain of thought prompt formulation. And in yellow, you have here the zero-shot chain of thought, so you know, argue step by step and everything that we already do in prompt engineering. Look, at common sense, there's no difference between those two at all. In soft reasoning, there is almost no difference between chain of thought and no chain of thought. So whenever you are not in the mathematical reasoning, but you are in the soft reasoning, in the normal human reasoning area, it doesn't make any difference if you use chain of thought or not, is what Princeton, Hopkins and University of Texas found. Knowledge, there's a little bit of improvement if you go with a chain of thought, but I don't know if this is really important. But of course, where you see the difference is again mathematical formulas and symbolic reasoning. So you see, those are the only two objects here, more or less, where chain of thought, according to this brand new study, is beneficial. Interesting to know. I did not know that fact. But there's a third paper, something looming in the dark, and this paper is much more frightening because it goes deep. It goes down to the root of our reinforcement learning. It goes to the base of our pre-training of our language model, and this is really something that a lot of people get completely wrong. They do not understand what is the main point of this study because it's so easy to just go here with the surface results. But since you're here on this science channel, you deserve more. So let's look at this paper. September 20th, 2024, Google DeepMind publishes here training LLMs to self-correct via reinforcement learning. And this is a highly interesting paper. And if you look at this, they say here, and they say, to build SCoRe, we first show that variants of our supervised fine-tuning on offline model-generated correction traces are insufficient for instilling self-correction behavior. And Google says, in particular, we observe that training via supervised fine-tuning either suffers from a distribution mismatch between the training data and the model's own responses, or implicitly prefers only a certain mode of correction behavior, and this certain singular mode of correction is often not effective at test time. So this is why self-correct fails. And this is a sentence that is quite heavy because, reading the latest AI research paper, what is the beauty? You immediately understand what the actual models, the actual implementations in code that are running today, where they fail. What are the limitations of those models that were implemented just yesterday? Because the research paper look exactly and they analyze what is exactly the current state of technology. What are the factors and why do those models that we have today fail, and how can we develop the models of tomorrow? So the more you read the research paper, the more you understand what current implementation fail on. And to formulate it here for my green grasshoppers in green, self-correction of LLM, they have a bad performance. So the question is, how can we improve this? And some people say, this is what a coincidence that with the appearance here of OpenAI o1, the strawberry model, that suddenly has a better performance. Interesting that Google comes out now with this kind of series of insights how to improve with the self-correctness of those models with reinforcement learning. And if you think that some strawberry task take up to, 37 seconds, up to 60 plus seconds. Yeah, there could theoretically be some self-correction going on here on the latest OpenAI models. What a coincidence that Google helps us here to understand what is not working with all the other models and what could be done to overcome the current thresholds. So Google tells us here exactly the same. The main reason why traditional self-correcting reasoning approaches in our current LLMs, our best LLMs we have today, are in fact ineffective is due to a mode collapse and a distribution mismatch during the training phase. For my green grasshoppers, this means on your hyperplane, you have local minimas. Here local minima, here local minima. Somewhere else in the far distance you have another local minima. But those are only local minima. Your goal is to reach the global minimum because over there is the best solution. There is the best causal reasoning approach. But you are trapped here in a local minimum somewhere far, far away from the global minimum. So how to overcome this? If you're somewhere here down deep here, how can you jump out of your local minimum, travel over to the global minimum? If you want to see this, well, let's talk about it. So again, for my green grasshoppers, the summary, what are the key problems identified in current state-of-the-art, current technology, self-correcting reasoning, causal reasoning? We have the mode collapse, the distribution mismatch. We have a significant bias towards a safe response of the model, which is highly interesting. And we have a learning incorrect priorities. Now, I just want to look here at the local minimum trap, because I think this is the most important to understand here. And then we can talk about the model, how the model tries to overcome this limitation. So when our LLMs are fine-tuned using here SFT from Hugging Face, for example, or similar approaches, they tend to latch onto a trivial correction strategy. So instead of making meaningful corrections that are even a little bit more complex, the model may learn to make only minimal edits or even no changes at all, leading to a poor self-correction performance. So this behavior, this being trapped in your local minimum, can be seen as here exploring, not really exploring better correction strategies, because the model becomes biased towards making no substantial corrections. Because the model just wants to play safe, and it has been trained on to play safe. So, very strategic, very high-level explanation, but never mind, we will look at the mathematical details in about 5 minutes. So, the main reason why we need something else, because all our self-corrected causal reasoning, we are all trapped in a local minimum somewhere, and we are unable to get out of this local minimum. So all your causal reasoning will always be more or less on the same logical path. And you will not leave your local minimum because you don't know how to reach escape velocity to leave your local minimum behind. So, how can we reach escape velocity? Google's idea is now simple. I have 2 stages, and in the first stage I just prepare for the second stage, and the main action, if you want, is happening only in the second stage, but in the first stage I have the initialization for the second stage. Great. A little bit more formal, stage 1 acts here, if you want, as a pre-training phase that regularizes the model. You know how we do this by adding a callback-liable or divergent term. This means that stage 1 prevents the model from diverging too far from its original responses, while still allowing it to learn the potential for meaningful corrections in the second attempt. Now, the goal here is really only to stabilize the model's learning process and to prevent the model from being overly conservative or for modifying here the correct answers that are not even necessarily done. Stage 2, now the model is ready for reinforcement learning. But we do not go with a single term reinforcement learning, we go with multi-turn reinforcement learning we apply in parallel. So, where it is optimized to improve both first and second attempts of the model, and if you want, the key innovation is here to use here a specific reward shaping mechanism to bias the model towards making substantial corrections. So this substantial correction will allow us to reach escape velocity, that we can leave this gravity well behind us. The model is trained to correct mistakes from the first attempt while avoiding regressive behavior. This stage builds on the foundation from stage 1, enabling the model to explore more complex correction strategies while still maintaining stability, and we reach this stability through stage number 1. So you see, this is the main idea. Just, if it's too complicated, divide it up in 2 stages. Stage 1 has a clear goal, and stage 2 will help us to reach escape velocity. Great. Now, if you are me, I ask myself, hey, why constrain here the first attempts in stage 1? Why not go crazy already in stage 1 and do some, I don't know, some stochastic ways out? Why do we have to consolidate ourselves? Now, stage 1 is designed to gradually guide here the model towards making correction without introducing too much instability. This is what Google found. If the model were allowed to stray too far from the base model earlier on, it might over-explore, leading to random or erratic changes that could destabilize here the complete learning process. So this means by keeping now the first attempt of the model close to the original base model, the system can now ensure that the model doesn't regress and that the corrections are only tiny little bit incremental. Avoiding the model collapse, beautiful. So the model stays here with this idea within a sensible search space, focusing on improving its second attempt in a more meaningful, stabilized way, and we only have a gradual exploration. So, okay, I said, okay, now I understand why in stage 1 you try to be real close to your original solutions. Now that we understood the idea, now we understand why Google have chosen this stage 2 approach. Let's look at now the formal explanation. Let's define here stage 1 and stage 2, according to the published paper by Google. So stage 1, let's call it correction-centric model initialization. And what is the goal here? The goal is to pre-train a model initialization that is less prone to collapse and is better suited here to prepare here the model for further multi-turn reinforcement learning that's going to happen in stage 2. So in this stage, the model is trained to improve the second-term responses while ensuring the first attempt stays close to the base model prediction. The primary goal is here to teach the model how to improve upon its own responses without introducing some excessive deviations from the base performance. And you know how we do this? We regulate it through a KL-divergence constraint, which discourages, given here the specific parameters, the model from making here large changes from its first response. Stage 2, let's call it here the full multi-turn reinforcement learning with a very specific reward shaping. And this is important because the goal here is to further optimize the model's self-correction capabilities over multiple turns using now the full reinforcement learning dynamics, but now we have enough power to reach escape velocity from each and every local minimum. So reinforcement learning enters stage 2, where the model learns to optimize both the attempts, first and second, and the learning process in this stage is designed, if you want, now by this reward shaping. And this reward is now a technique that biases the model towards making more meaningful, stronger corrections. And now we can afford this in stage 2 because we stabilize the learning process in stage 1. Otherwise, the system would just blow off. So this reward shaping for my little green grasshoppers here, this is a reward bonus. Think about this. A bonus is introduced during the second attempt to emphasize here meaningful corrections. So this means the system wants you to do corrections. It says, yeah, be brave, do some significant corrections. And this bonus is structured to give higher rewards for correcting incorrect first responses. And this mathematical formula, we're going to have a look at in a minute, biases the model towards improving the second response, but and now this is crucial, without degrading the correctness of the first response. So you see, escape velocity. Beautiful. Okay, this was my personal introduction. I hope I make it now a little bit easier. That now, if we look at the formal definition now of Google's idea, that you have the background understanding what we are doing and why we are doing it. So for my green grasshoppers, SCoRe, this new Google methodology, tackles this issue by using reward shaping and multi-turn reinforcement learning to push the model out of its local minimum, please, these are my words, and encourage here a more effective self-correction strategies. Be more brave. In this multi-turn reinforcement learning, instead of training here on the static traces that we have in the classical way, now we utilize a multi-turn reinforcement learning. The beauty is here, we do it on self-generated data, which allows the model to continuously update its correction strategy based on its own outputs. And this process helped reduce now the distribution mismatch between the training and the test phase. And now you see this is exactly the way how we solved the second main problem that we had at the very beginning. We had a distribution mismatch. And this particular idea by Google is now the solution to this particular problem. Great. On we go. Yeah, standard training, and here is SCoRe. Beautiful. If you really want to understand this, especially my little green grasshoppers, I would highly recommend you have a look at this paper before you try to go into mathematical solution and in the coding of the mathematical solution. There's a beautiful paper here by Cohere. It is called Back to Basics. It's really highly recommended, revisiting here reinforced style optimization for learning from human feedbacks in LLM. And we will use here exactly the reinforced optimization technique here in SCoRe. So therefore, let's have a look, because there is some beautiful summary here in this paper by Cohere. And here, if you look at paragraph 2, you have here 3 specific stages. And those stages are exactly what we will work with. Now, they looked here at the original reinforcement learning by human feedback pipeline proposed by Ziegler in 2020. Beautiful. So we do have the supervised fine-tuning stage, where a pre-trained language model is instruction-tuned using a dataset consistent of a given instruction prompt and a human written completion, and the policy is trained with a cross-entropy loss over the completion only. And this SFT model here, normally used here as pi, is used to initialize both the reward model here and the policy. Now, at the second step, the reward model stage here, we leverage now a reward model trained using here a data set of preferences, where y plus and y minus denote the preferred and the not preferred completion of a specific prompt structure. The reward model is trained as a binary classifier with the following loss function, where sigma denotes here our logistic function. And then this is what we are now looking at. The reinforcement stage, but remember, this is a single turn. We have to increase the complexity, but let's solve here, or remember here, the single turn ORL. The reward model is used to provide an online feedback in the optimization of the policy with the following objective. And this formula 2 here, this is the formula we're going to work with. But now you will understand why we will modify this formula, for what reasons. So let's go to the paper, now to the latest paper by Google. And you will find here exactly this formula from 2020. And Google says now, hey, we aim to find a model pi, or policy, mapping a sequence of input tokens to a sequence of output tokens. Easy. And it maximizes here the correctness reward obtained from the verifier at the end of some turns. Formally, this idea can be written as a following multi-step reinforcement objective. And you see here we have now this formula in the simplest form. And they say, note that unlike the standard supervised fine-tuning or the fine-tuning workflows that train the policy pi to directly produce an optimal response y for an input x, equation 1 trains pi over multiple turns, over multiple attempts simultaneously. And this is here the beauty here of this approach. And they say here, beautiful, we will use reinforce, as I showed you, with a Kullback-Leibler divergence penalty against this fixed model. And now such a policy gradient approach, train here policy pi theta to optimize here exactly here this formula. Pi reference is the reference anchor policy, typically chosen to be a pre-trained or SFT policy. Now we will take this and we will ask now the system, and we will try to understand it and ask here how the optimization is done. Because, and now to the main part here, you remember here stage 2, this is the real formula that we're going to try to solve. So to do so, we explicitly fine-tune the base model to produce a high reward revision at the second attempt, while forcing the model to not change its first attempt. You know this now. Possible, then is the base using Kullback-Leibler divergence. While does this appear suboptimal? The first attempt response with fewer mistakes could be corrected to a better second attempt response. But as we will show, this stage is critical in reducing the base model bias towards simply coupling the first and second attempt distribution, thus becoming trapped in the local optima or minima. So now you understand. If you would have started with this sentence, you would have said, what? But now I hope with the explanation you understand what's going on if you actually turn on this multi-turn reinforcement learning. So our objective now that we now have to optimize is now this beautiful equation number 3. Yes, you know, we have a beta 1 and a beta 2. Those are the hyperparameters to enforce a strict Hubert-Leiber penalty. You have it either on the first attempt or on the shift or the second attempt, whatever. But this is not so important. I just wanted you to understand here the main concept, because this is what we will code. If you try to code something, this is your equation. Beautiful. Okay, let's go here to the official paper by Google, and you see here in figure 6, stage 1, stage 2. Now in Google's way of explaining this, maybe you like more Google's way, go with this one. Stage 1, train an initialization for the self-correction. You have here maximize the reward in the second attempt. In the stage 2, run a multi-turn reinforcement learning with this reward shaping and maximize the shape reward of the second attempt within this SCoRe model. Great. So, what have we achieved? We avoided the distribution mismatch and the collapse of the whole complex, because we were training here on the model's own distribution of the correction traces. So this new Google SCoRe mitigates here the issue of distribution mismatch inherently in offline supervised fine-tuning, and using here the regularization technique with the Hubert-Leiber divergence in a particular way, in a multi-turn, multi-parallel way, we prevent the model from defaulting to ineffective correction strategies, ensuring that the model will learn something brand new. Great. I have prepared here some presentation on OpenAI 01 preview, and I did some simulation. Let me show you in real time. So we're here now live in ChatGPT 01 in the preview, and I already uploaded the paper and I did some simulation already with 01. And now I say, hey, can you provide me with a short, simple example that runs exactly through all the simulated steps that we just did here in the past that I explained to you already in this video. So can I see now the method working here in real time? And 01 comes back and says, certainly, let's walk through a simple step-by-step example that demonstrates here exactly how SCoRe methodology functions in practice. So we have here the prompt, calculate the sum of the first 5 positive integers, real complicated, but I want a simple example. So stage 1, initialization with the regularization. You know, objective, train the model to make significant corrections in the second attempt while keeping the first attempt similar to the base model. Now I've told you 3 times, now you remember this in your dreams. So, initial response is, I say, hey, the sum of the first positive integers is, sum up is 14, and you know that it is 15. So now we go to the second turn, so the self-correction with the instruction. And you say, hey, there might be an error in the solution above. Please review your calculation and correct any mistakes. And 01 goes back and says here now, oh, apology for the mistake. The sum of the first positive integer is, of course, 15 and not 14. So, training with regularization. The first attempt is kept close to the base model distribution to prevent it from changing drastically. And then in the second attempt, the model is encouraged to produce higher quality corrections. And we want those corrections. We do here give some extra bonus reward for doing these high quality corrections. Now we enter stage 2, the reinforcement learning with the reward shaping. Encourage the model to adopt a generalization of the self-correction strategy by rewarding improvements for the first to the second attempt. The policy definition with a policy pi theta, the model's behavior in generating the responses. The model's initial response, the sum of the first positive integers, is now 16. Wow, great. Second turn. There might be an error in the solution above. Please review your calculation. You notice now. And 01 comes back and says, you're right, I made a mistake. The correct is 15. Beautiful. Reward calculation. So we do have a reward function, and we have here the first attempt reward, incorrect answer, and the reward is 0. Now, if the second attempt reward, if this is correct, we give it a reward of +1. Plus, there's a simple formula to calculate the bonus. Because as told you, we want to say, yeah, please go, be brave. Try to find self-corrective versions that are correct. In the end, you will get a bonus reward. And this bonus reward is now, a simple formula, is now 3. Beautiful. So we have a policy update. From our reinforcement learning update, the model updates its policy parameters to maximize the expected cumulative reward. Focus increase the likelihood of making real effective corrections now in the second step that lead to a higher total reward. This is the whole idea of this shaping the reward to support here brave new corrections. Next example. What is the product of 4 and 6? My goodness, product of 4 and 6 is 20. Incorrectly calculates the product, and we go saying that there might be an error. Please review your calculations. And we have now you know it, this is incorrect 0, correct would be 1, and the bonus is 3, and we have an update, and beautiful. And you understand, this is, in the simplest example, how it does. Avoiding the collapse and ensuring generalization, reward shaping, regularization, beautiful final outcome. The model learns to effectively identify and correct its own mistakes. Then again, we have a summary of steps, beautiful. So 01 is really detailed, I like it. Key takeaways, wow, I didn't even ask for this. Self-generated data, exactly, the model learns from its own output, promoting autonomy and scalability. Also, if there's an inherent error, this inherent error will stay there. Multi-turn interaction, beautiful, multiple turns, parallel reasoning, reinforcement learning, regularization, and reward shaping. Now you know this technique. If I wake you up in the middle of the night, you say, yes, I know exactly why we use regularization and reward shaping in SCoRe. Beautiful. And then I told him, hey, I don't understand your point 5. I'm sorry. Point 5 is here the explicit policy update via the reinforcement learning. The model's parameter adjusted to maximize the expected rewards. And you understand that this could be a sensitive topic because maybe our little strawberry here is using some technology that might be a little bit similar to it. So I don't want to be kicked out here by an unfriendly strawberry. So I try to have here a friendly strawberry. So I say, hey, I'm sorry, can you help me? And then Strawberry comes back and says, hey, I'm sorry for any confusion regarding point 5. Let me provide a clearer explanation. And here we make a deep dive into the policy update via reinforcement learning. And it tells me how it works, collective rewards, first attempt, second attempt, you're now familiar with this, calculating the expected rewards, you know this, and now it gets interesting, updating the model parameter. So we use here policy gradient methodology, and the model updates its internal parameters with the goal to increase the likelihood of actions of responses that lead to higher rewards, to higher correction that lead immediately to the correct results. So we reinforce positive behavior, and the positive behavior in our case is try to reach escape velocity, be brave, get out of the local minimum. Iterative process. Then it gives me a simplified analogy. Imagine a student learning math problems, first try, gets it wrong, feedback, they check the work, realize there's a mistake and correct it. Reward, the teacher praises the correction effort more than if the student just had it guessed the right answer initially. And the learning happens, the student recognizes that a careful review and corrections are really valuable and starts applying this new strategy consistently to correct itself, read again, if this was the correct solution. It encourages self-correction, prevents trivial solution, generalizes to new problems. Key takeaways, yes, yes, yes. I hope this clarifies point 5 for you. And then you know me. I see. But imagine that the model does a second run to verify, but the complexity of the original query is high. It is really high. And even in this second run, in the verification run, the mistake is not detected by the model because it is inherently the same model that just generated this in the first place. So since the mistake now is in another complexity class above the current abilities of our model, but then this methodology will fail, no? This idea that Google had with step 1 and step 2 will fail. And O1 preview comes back and says, hey, you are correct. The SCoRe methodology is designed to enhance a model's ability to self-correct within the bounds of its existing knowledge and its existing reasoning capabilities. If the complexity of a query exceeds what a model can handle in its pre-training learned, the model may fail to detect and correct its mistakes. So I have the same opinion. This is the reason why I ask it. But I think it's interesting that O1 preview is able to do this, because I tried the same thing with other models, and other models were not sure about this, that I am correct in my observation. So I do like my little strawberry. Strawberry goes on, says limitation due to model capacity, can only correct errors that it has the capacity to understand. And you have to understand, if you apply now Google's new methodology to a base LLM, that is a very tiny, 8 billion parameter LLM, that has been down quantized to, 8-bit or 4-bit, you have to make sure that the complexity level that this model is able to solve is within your query complexity, your task complexity. It doesn't make sense if you go for a cheap model that you only pay, $5, but the model is not able, the model does not have the complexity solution necessary to solve the query. So therefore, make some tests before you start your main task that might run for some time and might cost you more than $1 or $2. Great. Reasoning abilities, yes. Implications, failure to correct. Of course, if the model lacks the knowledge or the reasoning skills, it might not detect the error in the second attempt, leading to a failure in self-correction, and the whole self-correction will fail. Beautiful. Therefore, it is necessary to have those powerful O1s, these powerful strawberries or whatever will come up in the future, who do have a complexity reasoning capability that are able to solve a given task. Possible mitigations, real nice, further training, enhance the model training with more data relevant to the complex domain so that you can improve the understanding, go on with pre-training, do a lot of fine-tuning but focus on continued pre-training, use specialized models here that can tackle your complex queries in real narrow domain, then maybe an 8B model might be successful, or simply use tools. This is one of the best ways. Have a model that allows you for tool use. So you have a Python interpreter or whatever you go with to simply do a computer simulation or computer calculation to find the solution. Summary. SCoRe enhances model's ability to self-correct within its existing capabilities, but doesn't equip it to handle queries that are fundamentally too complex or outside of its knowledge domain. No way. And don't even ask me if you can use reg. No, it will not help you. My goodness. And then, friendly as I am, I said, hey, why did you hide the Kullback-Leibler divergence from me in the simplified explanations? So, you see, the model here was very, very general. No details, just some very plain surface level explanation. But now I want to learn. I need a little bit more of a deep dive. So I say, hey, why you hide your Kullback-Leibler from me? Can you not provide the details, or can you provide the details? And my little strawberry comes back and says, hey, you're absolutely right, and I apologize for not including the Kullback-Leibler divergence in the earlier simplified explanation. So you see, even if you get in the first hand here this simple explanation, don't stop there. Ask the system, hey, this is nice, but come on, let's do a deep dive. Let's show me here the real argumentation. Let's show me the formula. Let's go through the logic step by step. If you use some arithmetic or symbolic reasoning. Yes, I also do learn. Okay, so here we go now, and now my little strawberry comes back and tells me, okay, we have here the overview of SCoRe, stage 1, stage 2. Now you know this, I don't have to explain you anything about this. And now mathematical formulation. Now it gets interesting. It says, okay, so we have a notation. P theta, the policy of the model parameterized by theta. The input is x. The model's response in the first attempt is y1. The model's response in the second attempt, you're not going to believe it, is y2. The reward function is called r. Unbelievable. And Kuhlberg-Leiber divergence measuring the difference between two probability distribution, as always, is here D for distribution or divergence in Kuhlberg-Leiber. And then we have beta 1 and beta 2, the regularization coefficients that you can play around. And then you remember the formulas I showed you here from this back to basics? Here we go. So stage 1, initialization with the regularization. Now this is exactly what we have to solve, and then what you will code optimizes here the following objectives during stage 1, and here we go. First attempt regularization, Kuhlberg-Leiber penalty, purpose. Second attempt focus, why this matters. We want to avoid the collapse, improve the coverage. Stage 2, multi-turn reinforcement learning with reward shaping. Now we have here a beautiful explanation, optimize the following objective during stage 2. Yes, it does fit here in one line, we are lucky, but look at this. And then we have this reward. This is here important, and we will come back to this formula. And then we have the reward shaping with the bonus. Here, this is the shaped reward. This is the formula, real simple. Penalty, problem shaping is important. I explained this to you. So you see, now our little O1 preview is able to give us exactly here the details from the paper. I have 3 papers in total here in the background here uploaded to O1. So you see the rule of the Kuhlberg-Leiber divergence in SCoRe here. First attempt regularization beta 2. Yes, yes, yes. I scroll over this, I already explained this to you. And now it comes up interestingly, and I have in my system prompt, try, if you have some complex explanation, try to give me at the end of the theory, try to give me here a real example and run through the example. And now this is here from my system prompt that Strawberry comes back and says, hey, let's revisit the previous example with the mathematical detail now included in here. Calculate the sum of the first 5 positive integers. Now we have here Kuhlberg-Leiber penalty. Yes, second attempt. We have now the reward calculation, the objective that we have to maximize. First attempt, second attempt, reward. Model's response. Yes, total shaped reward policy update. Yes, I scroll over this. I already explained this to you. We have a summary of the method, real nice. Nobody asked for the summary, but it is provided here by our little Strawberry. Stage 1 objective, train the initial policy that maintains the base model's behavior in the first attempt and focus on correcting errors in the second attempt that are real close. However, you have a strong penalty, beta 2 on the first attempt to prevent any deviation. And you have a policy less prone to collapse into trivial solution. This is beautiful. This is why we restrict ourselves in stage 1. But in stage 1, we break out, we reach here escape velocity. With reward shaping, we have a smaller coefficient beta 1 to both attempts to ensure stability. Conclusion, prevent collapse, balance exploration and stability, and enables efficient self-correction. Beautiful. And then I hope this detailed explanation clarifies the rule of the Kuhlberg-Leiber divergence and the SCoRe methodology. Let me know if you have any other questions, and of course I have other questions. I'm also thought for 26 seconds here, and I said, hey, please be so kind to explain the formula that you show so I can understand better. Like the one objective during the stage 1, so I tell him, hey, this is the one that I want you to start with, and as you can see, it took him half a minute to come up here to check, to understand all the parameters and then explain the formulas. So if you don't understand anything in any paper with my little Strawberry preview, and this is my test, but do your own tests, and maybe give me a feedback. Let's have a look what came out. So stage 1, initialization with regularization. This is our objective function that we have here to maximize. This is it that I showed you now 3 times already. Now Strawberry says explanation of the formula. Let's break down this formula step by step. Verbose notation, parameter, model policy, x, y1, y2, y star, ground truth, the reward function, beta 2, Kuhlberg-Leiber, reference policy. The maximization objective, we aim to find a model parameters theta that maximizes the expected value of the expression inside the bracket. We are trying to optimize the model so it performs better according to our objective. The expected value E, yes, expected means we are averaging over all possible inputs X and over the possible responses Y1 and Y2 that the model could generate according to the policy. We do the sampling here, beautiful. Then we look at the expression inside the brackets, nice. And they really explain, look, this really goes here term 1, and then the second term here with the Kullback-Leibler. This is the penalty term that subtracts from the reward. You have the Kullback-Leibler divergence penalty, model distribution. It's the scaling factor beta 2 determines the strength of this penalty, and the purpose of this penalty is explained to you. Real nice. This is real nice. Intuition behind the objective. I mean, the training data that O1 preview was trained on is really first class, okay? We want to maximize the second attempt quality. You know this by now. You want to regularize the first attempt, and you want to have a balance between the reward and the penalty. You know this. Another practical example to illustrate the formula. Ground truth is 15, okay, first attempt, 14, penalty, second attempt, now we know the mathematical formulas, okay, compute the overall objective, beautiful, importance of each term, now you know these terms, maybe a little bit of a repetition, okay, role of beta 2, the regularization coefficient, adjusting beta 2, a higher beta 2 places more emphasis on keeping the first attempt close to the base model, a lower beta 2 allows for more deviation in the first attempt. And this is not easy. You have to play around with these parameters if you do the real calculation, because there is no logic that you understand at what exact parameters you have to put those beta parameters. You just have this, it's a try and error goal. Connection to the SCoRe methodology, stage 1 goal, stage preventing the collapse, encouraging self-correction. It really understood here the core idea of this methodology. Summary of the formula, purpose, maximize the correctness of the second attempt, regularize the first attempt, balance between exploration and stability. Key takeaways, the formula presents a trade-off, reward and penalty. Optimizing the objective, the model learns to keep its initial response similar, focus on improving the answer through self-correction. If you have more questions, no, this is it for this part of the video. So this is the first introduction here. I think O1 preview, the first model I have to tell you that I personally experienced this detailed information in the explanation, understanding here the scientific notation here to the last comma. Real nice. So try it out yourself. If you have access, try to get familiar with this. But I think now O1 preview, this is now really a tool I can use if I want to, I don't know, upload 5 or 10 papers, that I'm really able, that I can kind of trust my AI system, this little strawberry, that it really gets the scientific notation right and it gets the main idea right. Of course, this is only one test. One test is not statistically significant at all. So this might be just once in a lifetime that it got it right. So therefore, hey, AI community, what are your experiences here with Strawberry? You find it helpful? Do you see any problems at all? Let's share this in the community so we can all learn how to optimize our interface here with O1 preview. Okay, this is it for this video. I hope you found it informative. Maybe you got some new ideas. You had discovered some new research here by the scientific community. And it would be great to see you in my next video.